This is the last part for designing a flat plate slab system using direct design method. As we have already discussed that a flat plate slab system is a one in which the slab is resting directly on columns. It is very clear from this image that the slab is resting directly on these columns without having any interior beams. The difference between a flat slab and flat plate slab is being explained in this slide, as already discussed, that if there are some drop panels and column capital, this will make a flat slab systems, and if these two elements are absent, then the system becomes a flat plate slab systems. Here this figure 2b, it's a flat slab system. You can see that there are drop panels and column capitals. These are the new additional elements in the load path of this structural system. And this one in figure 2a, this is flat plate slab system. You can see directly that the slab is resting directly on columns. In our previous discussion, we have understood the reasons for providing these drop panels and column capitals, as these slab systems undergo a failure called punching shear. So in order to avoid this kind of failure, drop panels and column capitals were provided in the flat plate slab system, and this converted this system into a flat slab system. So in case of flat plate systems, because these elements are absent, so you have to provide a special shear reinforcement which is called shear head reinforcement, which has been shown here. So absence of drop panel and column capitals will now be compensated by this special kind of shear reinforcement. These are the same steps which we have already discussed while designing a conventional slab beam system using direct design methods. The next we have the limitations. This is a critical statement for this flat plate slab system. We have a total area of 4500 square feet, which has been divided into 25 panels as discussed previously. Now the panel sizes are 15 cross 12 feet. Concrete strength is given, the steel yield strength 50,000. Service live load is 60 psf. This will be required in order to calculate the total factor static moments. All columns are rectangular, 12 inch in long direction. These are rectangular, no more square columns. These are rectangular, which means they have a different value of length and width. So they have 12 inch in long direction and 10 inch in short directions. So the long direction for this panel is 15 and the short direction is 12. We will discuss it later. Primly slab thickness is set as 5.5 inches. It is different from the previous example which we have covered for conventional slab beam systems. But we will do the same step here. We will going to check the provided slab thickness of 5.5 inches against the code provisions. It is also given that no edge beams are used along the exterior edges. So as discussed, that flat slabs and flat plate slabs both don't have interior beams, but they may have exterior beams. So in this numerical, it is given that there are no edge beams along the exterior edges. So what we are required to find, we have to find total factored static moment along the long and short directions in the typical flat plate slab systems. This is the first part of this whole numerical, that you have to find total factored static moment. This is the sketch. Because there are 25 panels, 5 panels, they are going at 15 feet center to center. The distance from this center to center here, it is 15 feet. And it will keep going on in this direction. You see there is a continuity line here. This is the continuity line here. Similarly, there is a continuity line here, because in this direction as well, we have 5 panels, but at 12 feet center to center. Each panel is 15 cross 12. So the dimension here is 15, and the other one, the dimension in this direction, it becomes 12. In the similar way, this is the long direction, this will become the short directions. So as we have given that the column size or column dimension in long direction is 12 inches and column dimension in short direction it is 10 inches, so it can be seen from here. This one is long direction. See, this is long direction. So in long directions we have 12 inches, whereas in short direction, this one is a short direction because this is 12 inches, this is 15 inches. So this one is short direction. In short direction, we have a column dimension equals to 10 inches. This has been given in the numerical. In addition to this, we have given the service loads, live loads have been given. So now move on towards calculating the total factor loads and total factor moments. Now because the slab is 5.5 inch thick, so it will have a self weight which is a dead weight, so we have to calculate the self weight of this 5.5 inch slab. So we have already discussed previously, like, or in order to find the self weight of a slab, you have to multiply the thickness with its density, but now because the density is in 150 pounds per feet cube, so it is being in feet, so you need to convert, when you are multiplying the thickness with this density, you have to convert this thickness into feet as well. That's why we have divided this 5.5 inch with the 12 in order to convert into feet. So the thickness multiplied by this is the thickness, this thickness is being multiplied by with density, so you have a self weight in 69 psf. This is an pressure load or area load. Now because we have the self weight or the dead weight, as well as we have given the live loads, so now we can find the total factor load. As I already told you, like when you are doing your numericals, you will use the factors 1.2 here, and for this you will gonna use 1.6, because these are the previous factors in ACI code which have now been revised. So 1.2 dead loads plus 1.6 live load So in dead loads, because we are not giving any kind of superimposed dead load, so we will consider only the self weight of the slab. So the self weight is 6.9 ksf. See, this is psf, so you have divided this one by 1000, divide this one by 1000 in order to convert this psf into ksf. Similarly, the live load was given in the numerical, that was 60 psf. So multiplying these two factors, we get the total factor load 198 psf. The next thing is to find total factor moment along each direction. So we will consider first the long direction. The formula will be same, 1 by 8 WUL to ln square. So when you are calculating along the long direction, so I'll just explain you first thing. So because this is the long direction, and for example you have like this is the equivalent rigid frame, so you are calculating for this one MA. So what will be MA? 1 by 8 into WU into L2 into Ln square. As previously discussed, that L2 is span perpendicular to the direction of the equivalent rigid frame. So when you are calculating the total factor moment for the equivalent rigid frame A, or equivalent rigid frame which is running in the long direction, so this dimension will become L2, and all the dimension in the direction of this equivalent rigid frame, these will be L1, and both these L1 and L2 will be center to center. However, in order to calculate Ln, this is again in the direction of the equivalent rigid frame, but this Ln is clear span, not center to center. So it's very clear that when I'm calculating total factor moment for the long direction, this is going the long direction, this is the long direction. So for this long direction, L2 will be this dimension, which is equal to 12 feet. And for calculating Ln, this will be the center to center span, which is 15 feet. So out of 15 feet, I need to subtract half column dimension from here, similarly half column dimension from here. And this half width is basically 6 inch from this side and 6 inch from this side. So overall you need to subtract 12 inches from 15 feet. See, 1 by 8 WU, this is total factor load. This has been divided by 1000 in order to convert into KSF. Multiply by L2. L2 is 12, what we have discussed. For Ln, we have to subtract 12 inches or 1 feet from 15 feet. So it has been done here. So the total factor moment in long direction will come out to be 58.2 fit kips. Now for short direction, I'm going to explain you again. Now because this is the short direction, so the equivalent rigid frame would be running like this one. See, this is the equivalent rigid frame. And every dimension in the direction of this equivalent rigid frame will be considered as L1. Like this will be center to center, here will be L1, because the rigid frame is running here in this direction. And L2 will be span perpendicular to the direction of this equivalent rigid frame. So this will be L2 here. So for this part, L2 will be 15 feet, L1 will be 12 feet, but we don't need L1, we need Ln. So Ln will be equal to 12 feet, and you have to subtract what? You have to subtract this one, half dimension from here, and similarly half dimension, half width from here. So half width from here is 5 inches, because this overall is 10 inches and half will be 5 inch. 5 inch from here, 5 inch from here. So you need to subtract 10 inches from 12. See, this is L2, 15 feet, and for Ln we have subtracted from 12 a dimension of 10 inches. So 10 divided by 12, it will becomes 0.83, and then you have to take the square definitely. So after multiplying, you're gonna get the moment. So this is the first part, that you have calculated the total factored static moment in each of the two directions, the long direction and the short direction. These are the two moments. Now moving toward the second part of this numerical, we have been asked to review the slab thickness and the other nominal requirement for the dimension of flat plate design problems. So in the numerical, we are given a slab thickness of 5.5 inches. We have to check against code requirement, like the given slab thickness is satisfying, or we have to increase it. So because we know that if we are given a slab with beam systems, then we're going to focus on this table in order to find the minimum slab thickness. And if there is a slab system without beams, means a flat slab or a flat plate slab systems, then we have to consider this table 8.3.11 in order to calculate the minimum thickness. Now let us zoom this one, because we have to focus on this one. Here you can see that there are two different portions for drop panels and without drop panels. This first one is for flat slab systems, because a flat slab system is having a drop panels, and in case a slab system without beam is not having a drop panel, it becomes a flat plate system. So we have to concentrate ourselves in this portion, or on this portion. So it says that if your Fi here, this is Fi is 40,000 psi, and you are considering shear panels, your Fi is 40,000 psi, then a slab without edge beams, we don't have an edge beam in this numerical, so we'll concentrate on this portion. So for 40,000, this will be ln by 33. Similarly, if the Fi is 60,000, then you have to select ln by 33. This is for the exterior panel only. So now for present numerical, we are given the Fi is equal to 50,000 psi, which is in between this 40,000 and 60,000 psi. It is rightly in the mid of these two values. So because the system is without a drop panel, and if I'm to consider the exterior panels without the edge beams, then the formula will be in between this one. So I'm gonna use these two and take the average. Similarly for the interior panels, I'm gonna take the average of these three values. So just note down these two values. For exterior one, we're gonna use this one, and for interior, first we will gonna calculate Ln, which is the longer clear span. We have a panel of 15 cross 12, so this is the longer dimension, 15. So I will gonna subtract, we're gonna take the longer clear span, so 15 minus 12 inches, so 6 inch from each side, and it will gonna become 14 feet. So for minimum slab thickness, we have taken the average values First, for the exterior panel, the one I told you that we're going to take the average of these two values, and similarly for the interior panel you have to take the average of these two things. The values, the required thickness for exterior panel is coming out to be 5.34 inches, and the provided slab thickness is 5.5 inches, so it is satisfying the requirements. Again, for the interior panels, the required minimum slab thickness is 4.88 inches, and we are satisfying again this limitation because the provided thickness is 5.5 inches. The next part of this numerical is to compute the longitudinal moment for each of the 4 frames A, B, C, and D, which are running in the long and short directions. We have already discussed these things, that we have total of 5 locations at which we have to distribute this total factor static moments, and out of those 5 locations, the first 3 locations, the moment coefficients are taken from these cases, the one I have shown you right now, and the rest of the 2 locations, coefficient for the location at 4 and 5, these are the typical values which can be taken from this one. These are the typical values. This is for location 4 and this is for location 5, and the first 3, location 1, 2 and 3, these will be taken from the cases here. So now, because we have a flat plate system, so we have to choose one of the system here. So now let's see one by one. So you can see there is a masonry wall here, and because this is not matching our case, coming toward this one, it has exterior beam and interior beam. This is again not our present case. Looking at this figure, you can see this is the exterior panel and it don't have a beam. The slab is resting directly on a column, and in the interior panel the slab is again resting on a column directly, so it means it's a flat plate slab system and it is matching the current numerical. So we're going to use these coefficient 0.26 for the location 1, 0.52 for the location 2, 0.70 for the location 3. These are the coefficients for computing moment at the first 3 locations, and the rest of the 2 locations are the typical one. Just note down these 3 values. These are the values of total factored static moment for each of the equivalent rigid frame A, B, C and D. You don't need to require to calculate moment for B and D again, because we know that the total factored static moment for B is always half of the total factored static moment that has been computed for equivalent rigid frame A. Similarly, for the equivalent rigid frame D, this will be half of the value which is computed for C. So don't do the calculation repeatedly again and again. The figure is basically showing that this is the equivalent rigid frame A, this is the equivalent rigid frame B. So the total factored static moment M0 for A has been distributed at 5 locations, location 1, 2, 3, 4, 5. These are the 5 locations this which we have computed. So we have 3 coefficients for location 1, location 2 and location 3, and these are for the typical values. In the same way, the coefficient will remain same for the moment in B, but you have a different values here because the total factored static moment for B, equivalent rigid frame B, was half of equivalent rigid frame A. In other words, I can say that the value here will be always half of this one, here will be half of this one. So you have to draw this kind of figure. In the similar way, we had a computation being done for the equivalent rigid frame C and D, which are running in the shorter directions. This is again for location 1, this is for 2, this is location 3, 4 and 5, and definitely these are for moment in D and moment in C. So the value here 6, it is always half of this one. The half of 24 will be here. These are the coefficients which have been taken from the cases. This was the total factored static moment for each of the 4 rigid frames. For location 1, the coefficient what we have selected from the case was 0.26. Similarly, the coefficient for location 2 was 0.52 from the cases. Then this is for 3. These two are the typical values. The fourth one is always 0.65 of m naught, and this is for 5.35 of m naught. So that this has been shown in tabular form, and previously I have shown you in graphical format. Now the next thing is for the flat plate design problem, because we have completed the longitudinal distribution of moment, the next thing is to do the transverse distribution, for which you need to have torsional constant C. We have this formula for calculating torsional constant C. The details are being given in the lecture of DDM for slab beam system, so I'm not going to repeat here. The difference here is because previously you have the beams running in long and short directions, so you were able to calculate the torsional constant for those edge beams running in long and short direction. But now, because in this particular numerical of flat plate slab system, we don't have any edge beams, so the code says even if you don't have an edge beam, you have to assume a beam. So you will gonna construct line parallel to the edges of your column, and this will serve as imaginary beams. For example, this is your column, so from the end of the column you're gonna extend lines, and for example this is your column, so you're gonna extend lines from here. So these will be imaginary beams here, although there are no beams here, but you're gonna assume. So the dimensions of these beams are very clear. They will have a depth equal to the slab thickness, means 5.5 inches. The beam will have a depth of 5.5 inches, and the width, it will be different for each of the two directions. The beams which are running in this direction, they will have a width equal to the this dimension of the column, which is equal to 12 inches. Similarly, the beam which is running in this direction, this will have a width equals to this dimension of the column, which is equal to 10 inches. So in this way we're gonna say these are the beams, or this is the beam. This is the beam which is running along short direction, because this is the short direction, you remember, and this was the long direction. So the beam which is running in long direction, this one, this will have a thickness of 5.5 inches and a width equal to 10 inches, the one shown here. Similarly, this beam which is running in this direction, which is the shorter direction, so the width will be equal to 12 inches and its thickness will be equal to slab thickness 5.5 inches. So you're going to compute torsional constant for each of this long and short direction beam. The calculations are shown here. These are the values for short beam and for long beam. These will be required in next slide in order to do the transverse distribution of these longitudinal moments. The next part is divide the 5 critical moments in each of the equivalent rigid frames A, B, C, D and shown figure into two parts, one for the half column strip or full column strips, and the other full half or middle strips, or two half middle strip for each of the column line for frame A and C. So in this problem we're going to do the transverse distribution for each of the locations. As you remember, for doing this transverse distribution we have to consider a table that will tell us the percentage of longitudinal moment that is going to a column strip. So we're going to use this table. We already have discussed, this is for location 1, the positive location, this is for location 2 and location 5, and this is for location 3 and location 4. The important thing note here is, because we don't have a longitudinal beams running, so the value of alpha will be equal to 0, so the product alpha into L2 over L1, this will be always equal to 0 for us. So we're not going to use this one. if we have to distribute the longitudinal moments at location 1, we're going to concentrate at this part or these rows only. We'll calculate the value of beta t, and depending upon the value of beta t, we're going to do the interpolation as been done previously in the lectures of DDM for slab beam conventional system. Similarly, in case of transverse distribution for the positive moment or moments at the location 2 and 5, we have again two rows, but because alpha into L2 or L1 is 0 for our present case, so we're not going to use this one. We're just going to do interpolation here. Similarly, for location 3 and 4, we're not going to use this one because alpha into L2 or L1 will be equal to 0 for present case. Let's see this one. See, it's been clearly written in the notes as well that alpha into L2 or L1 is equal to 0 when there is no interior beam in the direction of strip under consideration. So we don't have interior beams, that's why alpha into L2 or L1 is equal to 0. In the previous numerical of designing conventional slab beam system using DDM, we have used these values because alpha into L2 or L1 was not equal to 0 because that system was having interior and exterior beam both. For this flat slab and flat plate slabs, we don't have interior beams, so this product will always be equal to 0. So this is the table which have been formed for each of these things. I'm just going to explain a few things. The rest of them are similar to what we have explained in previous numericals of designing conventional slab beam system using DDM. At location 5, there is calculation done for moment of inertia of slab in beta t. It's very simple. The formula is 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 equal to BH cube by 12. So for rigid frame A and B, the value of width B will be taken as 12 feet multiplied by 12 to convert into inches, and the value of H will be 5.5 inches because now the slab thickness is 5.5 given in the numerical. Similarly, if you are doing calculation for C and D for moment of inertia of slab, the formula will be same. You have to find BH cube by 12 for rigid frame C and D, which are running in short directions. So the value of B will be equivalent to 15 feet or 15 multiplied by 12 in order to convert into inches, and the value of H will be equals to 5.5 inches. So these are moment of inertias calculated for A, B, C and D. You remember, while you are calculating moment of inertia of slab, it will be different for A and B, but when you are calculating it for beta t, transverse distribution, you don't need to repeat it for B. The value which has been calculated for A, it will be remain same for B. Similarly, the value calculated for C will be same for D. These are the percentages shown here for the moments which have been distributed to column strips. At row 10, this is a transverse distribution of exterior negative moment, means for location 1. So for location 1, 98.8% will gonna go to a column strip and the rest will gonna go to middle strip. Similarly, the 11th row is showing you the percentage distribution of positive moment, means for location 2 and location 5. This will be the percentages. And the row 12, this is showing you the percentage distribution at interior negative moment, that is for location 3 and location 4. These are the percentage of moment which is going to column strip. The rest of the amount will gonna go to middle strip is in the same way. For example, if 75% is going to column strip, means 25% of this moment will gonna go to a middle strip. So now this is again the summary. That first thing, you find total factored static moment, then you do the longitudinal distribution of this moment, and in the very end you're gonna do the transverse distribution. This is the graphical summary. The last part of this numerical is to investigate the shear strength of the two-way floor systems. Here we will check two kinds of shear failure. One is called wide beam shear failure or one-way shear, and the other one is two-way shear, which is called punching shear. The phenomena of these failure is very similar to one which is experienced in case of footings, except in this case it is an inverted situation, because now the loads are acting in gravity from top, whereas in case of footings the load or the pressure load from the soil is acting from downward side. Let's go through the theory. I just highlighted some of the important points here. So the first kind of shear failure which we have to check in case of two-way floor system is wide beam actions, which is also known as one-way shear. The value of shear strength is equivalent to 2 under root FC dash into BW into D. The other kind of shear action is two-way action, which is also known as a punching shear failure. We have three different formulas given by ACI, and the smallest value of BC is to be chosen as a shear strength for two-way action. Normally the equation 23 here, this usually holds. The variable in all these three equations have been explained here. The code says that even when a shear reinforcement is provided, then the nominal shear strength, which is a combined effect of both the shear strength provided by the concrete and the shear strength provided by shear reinforcement, it should not exceed 600 root FC dash B naught into D. This is the same numerical which we were doing, so the last part will be covered here, in which we will gonna investigate the shear strength considering both wide beam action and two-way actions in this flat plate slab system. First we will gonna calculate the average value of D, because this is one of the things which we will require in order to calculate both one-way and two-way shear actions. Because the given slab thickness was 5.5 inches, so you're gonna subtract the clear cover 0.75 which we have assumed, and because there was a number 4 bar, so you have subtracted the dia of this bar. Ultimately you get the value of this average D, which is now equal to 4.25 inches. After calculating the value of average D, we're gonna make the critical sections for each of the two cases. For case of a wide beam action or one-way shear, if you remember in case of footings, we make the critical section at a distance D from the face of the support, whereas in case of two-way action, the critical parameter is being formed by making an offset D by 2 from each face of the column. So now look at this wide beam action first. Because we had a value of D equal to 4.25 inches, so from the face of this column, we're gonna make a critical section, the one shown here, 1 this critical section is at a distance 4.25 from the face of this column. So you're gonna calculate the rest of the dimension here, because the total dimension here is 15 feet. So you're gonna subtract the remaining dimension and you're gonna get 6.65 feet. In order to calculate the one-way shear this slab will be experiencing, you have to multiply the floor loads or the pressure load which you have calculated in step 1, which was WU, total factor load, which was 198 PSF. This has been divided by 1000 to convert into kip/foot square. So you will multiply this factor load with this area here, which I'm highlighting right now. So the dimension here, this is 6.65, and the other dimension is 12 feet. So 12 multiplied by 6.65 and you're gonna get 15.8 kips. This is the amount of one-way shear this floor experience. Now we're gonna check what is the one-way shear strength. So the formula is phi VC. Please note down that the value of phi taken here is 0.85. This is the old value. You have to consider the new value of shear coefficient as per ACA, that is 0.75. The rest of the calculation will remain the same. Phi into 2 into under root FC dash. I'm just going to write the formula here for you. Phi into 2 into under root FC dash into B into D. This is the formula for calculating one-way shear strength. So this is phi 2 under root FC dash into B into D. Because the value of width here is 12 feet, you cannot take in 12 feet because this is in PSI. So you have to multiply this with 12 again in order to convert this 12 feet width into inches. Multiply by D, which is effective depth, already calculated previously, 4.25 inches. Divided all this by 1000 in order to convert into kips. So you have the value 65.8 kips. Now because the shear strength is higher than the value of shear which the slab is experiencing, so the check is okay. Now moving towards the second step in order to investigate two-way action. Now here the critical parameter is at a distance d by 2 from face of the column. So you're going to make a critical parameter, the one shown here with the dotted line here, and then you're going to multiply the floor area loads with all this hashed portion which is outside this dotted line. So this is the floor load again here. You have to multiply this floor loads or the pressure area loads with an area which is lying outside this dotted lines. So first you're going to multiply this 15 feet and 12 feet. You're going to get the total area, and from this total area you're going to subtract the inner side. So I'm just going to explain you like this one. For example, this is your whole area, this is your column, and this is your critical perimeter somewhere here. So you just need to multiply the floor load with this portion. And how you can find, you're just going to take complete first area, and then from this area you're going to subtract this dotted one. So the dotted area is 1.35 into 1.19. It's been shown in the previous slides. All these dimensions are in feet. This 1.35, it is basically equals to 16.25, and the dimension 1.19 is 14.25 inches. I'll just want to explain how this has been calculated. Just look at here. Now because the column dimension in this way is 12 inches, it's 12 inches, so you have to go d by 2 from one side and d by 2 at the other side. Or you can say this dimension, this is basically equal to column dimension in this direction plus d by 2 on one face and d by 2 on the other face. So 12 inches plus d by 2 plus d by 2 you can write as d. So 12 plus d, this one is 12 plus d. In the similar way, the column dimension here plus d. So 12 inches plus d, the value of d is 4.25, this becomes 16.25. In the same way, the column dimension in the other way is 10 inches, and you have to add the value of d in that. So 10 plus 4.25 will give you 14.25 here. So basically the dimension values for these critical parameters are 16.25 and 14.25. These have been converted into feet in the next slide. Here these have been calculated in feet by dividing by 12. So this is the value of two-way shear this slab is experiencing. Now in order to calculate the value of two-way shear strength, we have the formula phi into 4 into under root FC dash B naught into D, where B naught is the perimeter of this critical area. Means you can find B naught here. If this is your area and this dimension is like C plus D, similarly in the other way this is again C plus D. If you have to take the perimeter, you're going to multiply this with 2, and you're going to multiply this with 2 again. This has been done here. See, 2 into 16.25. 16.25 is the horizontal dimension for this critical perimeter, and the 14.25 is the transverse direction for this critical perimeter. So B naught is coming out to be 61.0. So now 5 EC is equal to phi, you have to take it 0.75, 4 into under root fc dash. Now instead of 2 into under root fc dash, because this is two-way action, so the formula is this one, 4 under root fc dash. 4 under root fc dash b naught. Instead of now bw, there is now critical parameter b naught, which we have calculated here, b naught, and the value of d. Similarly, you have divided by 1000 to convert it to kips. So this is the two-way shear strength. Now compare this two-way shear strength with the value here. So it seems that there is no need of shear reinforcement for this interior location. This is the end of this numerical for the design of flat plate system using direct design method. Thank you for watching.